investigating the unexplained collapse of the Tay Bridge disaster. 1879, on the night of December 28, 1879, a train began its routine, crossing over the River Tay in eastern Scotland. To the passengers inside, the bridge ahead represented progress, modernity, and human confidence in engineering. Stretching nearly 2 miles across the water, the Tay Bridge was the longest railway bridge in the world, a symbol of Victorian ambition and technological triumph. Minutes later, that symbol would collapse into darkness. A violent gale tore across the Firth of Tay as the train entered the bridge. Winds howled at a speed rarely recorded in the region, rattling carriages and bending metal. Witnesses on shore later described sparks and flashes of light high above the water, followed by a sudden, horrifying silence. In moments, the central spans of the bridge gave way, and the train vanished into the storm below. No passengers survived. At first, the disaster seemed incomprehensible. The Tay Bridge had been hailed as a marvel of modern engineering. Designed by Sir Thomas Bouch, it was intended to withstand extreme weather and the dynamic forces of passing trains. Its failure raised a terrifying question. How could a structure built to embody strength collapse so completely? Investigators soon turned their attention to the bridge's design. While innovative, the structure relied heavily on cast iron columns, a material strong under compression but dangerously brittle under tension. In calm conditions, the bridge performed as expected, but under lateral wind pressure, those same components became vulnerable. Gusts exerted forces that the design had underestimated, placing stress on joints never meant to flex. The bracing system, intended to stabilize the tall piers, proved inadequate. Many connections were poorly fitted, with bolts that did not fully engage the metal they were meant to secure. Some components showed signs of defects even before the bridge opened, yet construction pressures and confidence in the design allowed these issues to pass unchallenged. Human factors played a critical role. Sir Thomas Bouch was under immense pressure to deliver a groundbreaking structure on schedule and within budget. At the time, engineering calculations for wind loads were still evolving, and safety margins were often based on limited, empirical data. Decisions that seemed reasonable on paper failed to account for the unpredictable behavior of real storms acting on a structure of unprecedented scale. The environment delivered the final blow. The storm that night was not merely strong, it was chaotic. Gusts struck the bridge at varying angles, creating oscillations that stressed the iron framework repeatedly. Each gust weakened the structure incrementally until one critical failure triggered a chain reaction. Once a single span collapsed, the remaining sections could not redistribute the load, and the bridge failed catastrophically. The train itself became part of the problem. Its mass and movement added dynamic forces at the worst possible moment. As the locomotive advanced into the weakened section, it may have accelerated the collapse, pulling the structure apart rather than allowing it to fail gradually. When daylight revealed the wreckage, the scale of the disaster shocked the nation. Twisted iron lay scattered in the water. Carriages were submerged and broken beyond recognition. The bridge that had stood as a monument to progress was now a warning. The official inquiry was ruthless in its findings. It concluded that the bridge had been badly designed, poorly constructed, and inadequately maintained. Sir Thomas Bouch's reputation was destroyed, and he died just over a year later, his career overshadowed by the catastrophe. The disaster forced engineers across Britain to reconsider assumptions about materials, wind loads, and structural redundancy. Yet questions lingered. Some witnesses insisted they saw sparks or flames before the collapse, suggesting electrical or mechanical failure. Others debated whether the train should have been allowed to cross in such severe weather. While these theories never displaced the core findings, they added layers of uncertainty that continued to fuel discussion more than a century later. The Tay Bridge disaster marked a turning point in engineering history. It reshaped design standards, encouraged rigorous testing, and emphasized the importance of accounting for environmental forces that could not be controlled. Out of tragedy came safer practices, but at a devastating cost. Today, The ruins of the original bridge remain beneath the waters of the Firth of Tay, largely invisible to those who pass above the modern replacement. But its story endures as a reminder that innovation without humility can be fatal. The collapse of the Tay Bridge was not the result of a single flaw, but a convergence of ambition, miscalculation, and nature's unforgiving power. It stands as a silent lesson from the past, that even the most advanced designs can fail when confidence outpaces understanding, and that progress, when rushed, can exact a terrible human price.